Hey everyone, we're going to continue on with our discussion about momentum and impulse, and we're actually going to move on to the next part, which is all about impulse. So we just talked about momentum, which was kind of a way to talk to quantify how much motion an object has. Like I said, how hard it is and how hard it's going to be to change that object's motion. So now we're actually going to talk about what changing the momentum would have to entail. And that leads us into the discussion about impulse. Now, if I want to change an object's momentum, either to give it momentum or take that momentum away, I need to apply a certain amount of force over a set amount of time. The more force I apply, the more that object's momentum is going to change. But the longer I apply that same force, the more that momentum changes as well. So this is what we end up calling impulse, and it's going to be represented by a letter J. Of course, these are going to be I think this is probably the only unit where the symbol and what it's actually representing kind of don't really make too much sense. Well, with the exception of the rotation unit, but you'll see why that is in a second. So common examples of what an impulse would be, that could be something like a kick or a shove, a punch, a car crash, coming to some stop. Those are all different impulses. You're having a momentum change because a force is being applied over a certain amount of time. Now, this is actually going to lead us into a very, very important aspect of this entire unit. For a lot of these topics, you should start to notice that there is a calculation aspect, but there's also a conceptual aspect. Perfect example of this is in the projectiles unit. There is a lot of focus conceptually about the factors that would affect things like time in the air, how far an object goes, the relationship between the x and y direction. There was a really big focus on certain conceptual aspects. And in here, impulse has one of these concepts that are extremely important and are asked all the time. So just make sure that you pay attention. Now, what we're going to end up doing, this is the equation that we're going to use to find impulse. Now, you'll notice that this is colored really weird, so I want to explain this in a bit. So the first part, this delta P equals F delta T. This is the equation that's given to you on the reference table for the AP. Delta P in this case is being used to represent impulse. As I mentioned before, impulse is a change in momentum, so they're one and the same. You want to know the impulse on an object, it's the change in momentum. You get the change in momentum on an object, that's the impulse, same thing. So this is what's given to you on the reference table, and it comes from that definition of what impulse is. Now, if you'll notice, there's this other part, this with the blue J over here. This is actually what's given on the Regents reference table. Now, normally I wouldn't stress what's on the Regents reference table, but I feel like I have to because, as you know, at the end of the year, you are expected to take the Regents exam after you take the AP. So, well, not right after you take the AP, but after you're done with the AP, when you come back into the class, instead of just, having fun for the rest of the year, we actually are going to have to start switching gears and learning the Regents material. So you do need to know what's going to be on the Regents reference table. So if you are looking for the word, since they're going to be using the word impulse a lot more in the Regents class rather than in the AP, while it does get used, not as much, you want to make sure that you're aware of the symbol for impulse and the equation to look for. If you'll notice this part, this is what I call the extension, because of the fact that it's very common that the information they give you is force, time, mass, and velocity. I usually tell my students to just remember this extension because this is going to be what you're going to end up using a lot. One quick side note is this equation, this impulse equation, has actually been used before. If we look at this equation, divide the delta t over to the other side, we end up getting m delta v over delta t. And, well, delta v over delta t is acceleration, and I get force equals mass times acceleration. So technically, with the exception of needing to know how to find impulse, a lot of these questions can actually be solved using Newton's second law. Now, there is I also want to mention that because of this is actually why I said that momentum could be used in the units of Newton times seconds. It's typically used for impulse. A perfect example: Regents questions will typically have impulse be measured in Newton seconds and momentum be kilogram meters per second. This can lead to some confusion in some questions, since they'll give you the change in momentum and then ask for the impulse. They're the same numbers, but the units get switched and people think that you have to do some calculation. So that's why I just want to remind you that they are the same unit, and they're one and the same. Now, one thing I actually did want to lead into, as I said, this equation actually leads us into an extremely important aspect for the concept of this unit. And that's the fact that when you go into a collision and your momentum changes by some amount, the amount of force you feel is actually going to be related to how long you're in that collision for. So if you're driving your car at 60 miles an hour and you end up getting into an accident and your car stops, you're gonna end up experiencing more damage and more of an effect if you hit into a brick wall versus a giant snowbank. Well, why is that? According to this equation, there's an inverse relationship between force and time. In both cases, the impulse you felt was the same, because both cases your mass was the same and the change in velocity was the same. So the force that you feel is greater in the colliding with the wall scenario, because the time it takes for you to come into what that you're in contact with that wall for is much smaller. If you consider the case of slamming into a huge snowbank, it takes a while for that snowbank to finally slow you down. So for the snowbank, the time of contact is extremely high, meaning that the force is going to be very low. Another example of that: if you fall out of a 10-story window, if you end up landing on the concrete ground underneath, the concrete ground brings you to a stop immediately in a very short amount of time. So you feel the very small amount of time increases the amount of force that you experience dramatically. Compare that to what a lot of stunt actors do and stunt doubles do, where they actually fall onto giant pillows, or I shouldn't say pillows, but inflatable mattresses almost. In those cases, the inflatable will actually compress a lot and prolong the amount of time that you're in contact with it, the amount of time that you're slowing down, and therefore it decreases the force you feel. Going back to the car crashes, this is actually one of the reasons why, first, there are airbags within the car. The airbags are designed to prolong the time of contact, prolong the time for the collision. Increasing that time decreases the force that you feel. Another example: if you've ever wondered why a lot of cars tend to almost explode and get damaged over small fender benders, a lot of that actually comes from the fact of this concept. Back in the day when cars were first created, they were extremely sturdy, almost indestructible. While that was nice because people could actually get into an accident and only leave, or their car could leave with just some paint scratches, a lot of people were dying left and right from even the smallest of car accidents. And a lot of that had to do with the fact that because the cars were so indestructible and barely bent and broke, that the car crash happened very quickly in a very small amount of time, and therefore the people driving the car felt a tremendously large force, even with airbags. So cars are actually designed to have what's called a crumple zone, that the car actually compresses and crumples together as a way of prolonging that time. Cars are usually designed to have slightly longer fronts because of it. If we wanted to, we could easily compress the front of the car so that it's fairly flat, or at least streamlined. But we actually keep it designed in that blocky way for safety reasons. So this is actually a really huge aspect that you want to make sure that you remember, that this idea of impulse and the whole relationship between force and time are key factors as to why certain things are designed the way they were and why certain things happen the way they do. For example, another side scenario, if you try to go catch a ball, if you play baseball or lacrosse or any sport where a hard object can be thrown at you sometimes, uh, you may have attempted to catch the object in your hand without any sort of glove or safety equipment. And you may know that when you go to try to grab a projectile like that, one of the things that you do is you tend to cradle the ball backwards. You tend to move your hand once your hand touches the ball, you tend to move it backwards with the ball. And this is another example of increasing the time of contact, increasing how long you are slowing that ball to stop, and decreasing the force that your hand feels. So next time, if you ever do play a sport like that, attempt catching the ball without moving your hand back versus pulling it back, and you'll definitely feel a drastic difference. All right. So this is kind of saying the same thing that I said before. So just make sure that you kind of keep that in mind. I know I sounded like a broken record, but I want to try and make sure I'm constantly reinforcing this idea of inverse relationship between force and time. All right, let's do some practice questions. Pause video, work yourself, and we'll go over in a second. All right. So for here, since I'm looking for the average force, what I'm going to do is I'm going to use the Ft equals m delta v. Again, if you wanted to use the F net equals ma equation, no one's going to stop you. Plug the numbers in. Make sure that you convert this milliseconds into seconds by times it by 10 to the negative 3. And you end up getting 3,500 newtons. All right. Here's the next question. Pause the video, work yourself, and we'll go over in a second. Now the first question looks for the impulse. So again, impulse is that change in momentum. So I'm going to take the mass and multiply it by the change in velocity. So 0.4 times 30, and that gets me an impulse of 12 newton seconds. Afterwards, to find the time, not to find the time, but to find the force, I'm going to use the time and set it equal to Ft equals J. Once again, convert the milliseconds, and I end up getting 1,500 newtons. All right. Here's the next question. Pause the video, work yourself, and we'll go over in a second. All right. So the first part is just a nice recap from the first unit. Finding out how fast he's falling when he hits the ground. You could do one of two things. You could do conservation of energy, or in the case that I'm doing, I'm going to use the timeless equation. So I plug my numbers in to get v squared equals 900, or v equals 30 meters per second. So the stuntman is going to hit the ground at 30 meters per second. Now, answering B and C, these are actually both the same question. We want to find the amount of force required to bring them to rest. The only difference is the amount of time. So this is just a perfect example of that concept I mentioned about how the amount of time, changing that time will drastically change the force. So in the first case with the air-filled balloon, it's going to bring it to a stop in 1.5 seconds. So I set Ft equals m delta v, plug in the 1.5 in for the time, end up getting 1,600 newtons. All right. In the next case, what I'm going to end up doing is replace that 1.5 seconds with 10 milliseconds. Again, converting the milliseconds into seconds. And I'm getting Ft equals m delta v. and I ended up getting 240,000 newtons. So you could see that the force is drastically increased. Of course, a lot of that has to do with the fact that the time was drastically decreased by a factor of 100, but that force increasing by a factor of 100 is definitely a very big change. All right, so obviously from here we could easily see that this person is going to die, while this person is most likely going to survive. All right, here's the next question. Pause the video, work itself, and we'll go over a second. All right, so what we're going to end up doing is pretty much going back to the ft equals m delta v. Again, very repetitive. A lot of these equations and questions, when it's just impulse or just momentum, are very straightforward. It's really the next topic that ends up being the main drive of this unit. So take our numbers, make sure that we put in the change in speed, which is, or change in velocity. So 8 minus 4 gets us 4, and we end up getting that the force is 16 newtons. All right, and this should be the last question. So pause the video, work itself, and we'll go over in a second. All right, now this is where we have to be very careful. Now, there's no change in speed, but there is a change in direction. This is extremely important because for a lot of people, they may see this as v and this being v, and they'll say, oh, the change in velocity is v minus v, which is 0. But you have to remember that velocity is a vector, meaning this v is now negative. So when I do impulse equals m delta v, I'm going to do negative v for the final velocity minus the initial velocity of v. So that actually gets me negative 2 mv. That's pretty much it. If you end up making this one negative, it doesn't really matter. It doesn't explicitly give me a direction. So whether you put negative 2 mv or positive 2 mv, you would still get the right answer. And that's it. The next video, it's just going to be a very quick one about the graph relations. Just going to go through it. It's going to be probably only a few minutes. But I just want to make sure that the big takeaway from before, besides the equation of how to find impulse, was to make sure that you really focus on that concept about impulse, about how the force and time are inversely related anytime you're comparing two same collisions, essentially, where they're both starting at the same speed and coming to rest at the same speed, or vice versa, or something like that. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.